Alright, so exponentials and logs, we're going to show that they're inverses, and we're going to do a few little things involving using the base e. What we have is a derivation below here, and the important thing is that we have log to base e and e to the x are essentially inverses. And it's shown here. It's not essential that you know this, but it might you might find it interesting if you're wondering where it comes from. So pause the video and have a look at this derivation if you're interested. And the important fact that comes out of this derivation is, well, a couple of important facts really. Log to base e is more commonly written as ln, natural log of x. So natural logarithm is its name, and n for natural can help you remember that. So ln x is the same as log of x to base e. So we have e to the x and log to base e are inverses, and log to base e of x is often written as natural log x, or abbreviated to ln x. And this is summarized right here. So the notation f to the negative 1 meaning inverse doesn't mean reciprocal. So the inverse function of this original function here, if you're given f of x equals e to the x, the inverse of it is log x. Notice I just said log x2. It's the other abbreviation is verbal abbreviation. We often just say log x when we understand that the base is base e. Other times we might use the term log x and it might be base 10. So you've got to look at the context and pay attention. You might have noticed by now that your scientific or graphics calculators have these functions, and they have their own keys because they're very commonly used. Next we have a handy skill outlined here that I'd like you to consider closely and take notes. And this skill is shown through an example. And so we have an expression, an exponential expression, 5 to the 2x, and we want to write the equivalent to base e. I'd like you to consider this closely. What we do is we set the given function or the given expression, and we set that we want to have it to base e. So we need to use a different letter than x, so we've chosen to use y instead. It can be any letter that you like, however, just not x. So let's let 5 to the 2x equal e to the y, and what we do then is take logs of both sides. Remember, the logs have to be to the same base. Alternatively, you could have written here natural log 5 to the 2x equals natural log e to the y. It's an equivalent thing, so that's fine. So we use our log law number 3. So the 2x goes out the front on the left hand side and the y goes out the front on the right hand side of the equal sign. And a log of e to base e follows this log property here, and the result is 1. So that's a 1 there. So it's y times 1, or just y on the right hand side. Left hand side unaltered there on that step. So what's happening now is that they are using the calculator to evaluate an approximation for log of 5 to base e. Remember, you could use the natural log button on your calculator, so you would just type in natural log 5 and hit equals, and then you would get 1.6094, etc. The times 2 off the front changes that to 3.219, etc. There's the x. The right hand side is unchanged there. So basically we have a value for y, which is what we wanted, because e to the what is equivalent to 5 to the 2x. Well, e to the 3.219 is, and so we write our expression. Notice how it's approximately equal to. In these further examples, it's important to pause the video whenever you need to and rewind the video as appropriate. So in this situation here, we're going to do two questions where we're solving the following for x, and we're going to use natural logs as a way of doing that. So we're solving this initial equation here for x, 3 to the 2x minus 5 equals 7. Let's have a look at this one. The statement is written, and then we take natural logs to both sides. That's log to base e, in other words. And we're using the log properties we're familiar with by bringing the index out the front there. Nothing happens on the right hand side. And then we're dividing through by log 3 on both sides on this step here. On the following step we add 5 to both sides, and then we divide both sides by 2. Remember, every term has to be divided by 2, and we can evaluate that with the calculator, and we get approximately 3.3856. Solving the next one, we write down the given expression, and again we take logs of both sides. We apply the same log properties as before, and remember, natural log of e is 1, and we simply have a rearrangement happening in the next step where we take 1 off both sides and divide through by 4, and we get approximately 0.2699. Some different sorts of equations which follow a different pattern. We have solved these for x. So on the first instance we've got e to the 2x minus 6 equals e to the x, rearranging it to make the right hand side equals 0, and a clever little substitution, something to really take note of there. Okay, so we let e to the x equal u, and we can see we've got a quadratic that is easy to factorize, and through the null factor law we can solve that, and then sub back out again in terms of x, and you can see that we have e to the x equals 3. The other solution is not valid, so that is rejected because e to the x is always greater than 0. So we have e to the x equals 3. Take natural logs of both sides and apply our log law, which means the x will go to the front, and whenever you've got natural log of e we get 1, and basically we can rearrange and use our calculator to evaluate. In the final example, we're given this equation here. We have to solve for x once again, and like the last example, we set the right hand side equal to 0 by subtracting 4 from both sides. And here's a clever step, multiplying through by e to the x. Now, index laws, think about your index laws. E to the x times e to the x is e to the 2x. We've got to be good with our index laws, and it doesn't matter what the base is, whether it's e or something else. Okay, so another way of saying that would go from e to the x to e to the x all squared, which is e to the 2x, and this would add 1 to each of the powers there, and that would become 4, because you'd have e to the 0, which would become 1, so 4 by 1 is just 4, and multiply this by e to the x, you'd have minus 4e to the x. Okay, so we need to rearrange that, so we've got our nice quadratic form, and another little substitution there. We've got a perfect square, u must be 2, and that's fine because it creates e to the x, which is 2, which is greater than 0, and that is valid. Okay, in the final step, we're taking natural logs of both sides and then applying the same log properties where the x there ends up out the front, just like in all the other previous examples. We know log of e, natural log of e is 1, so we've got 1x or just x, and we evaluate log of 2, and that's approximately 0.6.